Alrighty guys, welcome. So this is our first online distance learning lesson, which is kind of cool. Okay, I am going to go through the PowerPoint just like we normally do in class. I'm going to write on the PowerPoint just like I normally do in class. And the beauty of it is, since you are able to go back and forth and view this as many times as you like, you are not required to take notes. So I'm still going to grade you normally on everything else, but notes is the one thing that I will not be grading while we distance learn. So let's get started. This is going to be lesson 10-1, day 1, and we are going to look at graphing parabolas. The first thing that we need to look at is from chapter 9, and I know it's been a couple of weeks since we've seen each other and since we've gone over factoring, but factoring is going to be a really important part of chapter 10 as well. So if you have your table, your chapter 9 factoring table, go ahead and take that out, but we are going to go through here our 6 methods of factoring and review how we do those. So my first example that we see here, the 4x squared plus 12x, this method, if we remember, is called the GCF method for greatest common factor. Remember, in this method, we break apart each of the terms. So for example, 4x squared becomes 2 times 2 times x, and then 12x squared becomes 2 times 2 times 3 times x. Then to find the greatest common factor, we circle what they both share. They both share a 2, they both share another 2, and they both share an x. So that means that my GCF, or my greatest common factor, is 4x. Inside of parentheses, I write what is left over. So notice from my first term, I have the x left over. From my second term, I have the 3 left over. And then I keep the sign, that's the plus. So there's my factored form using GCF. The second method that we talked about in chapter 9 is called combining. And as you notice here in combining, we have 2 factors that are completely identical, x minus 2, x minus 2. Everything has to be the same about them, even that minus. So in combining, what we do is we cross out one of those factors. So I'm going to cross out this first x minus 2. And the reason that it's called combining is because I combine what is left over. So I combine that x plus 3. I leave my other x minus 2. And there is my factored form. My third method of factoring is called grouping. And notice that this method only works when you have 4 terms, right? I have 1, 2, 3, 4. So no other methods of factoring have 4 terms. Potentially GCF could, but grouping has to have 4. So what we do for grouping is I put parentheses around the first 2 terms, and then I put parentheses around the last 2 terms. And now what I'm going to do is I'm actually going to GCF. So the first thing I'm going to do is GCF. So for my first set of parentheses, the GCF is x, and I'm left with x plus 1. For my second set of parentheses, the GCF is a positive 4, and I'm left with x plus 1. And now, if we notice, I have a grouping, I have a combining. So grouping is really a combination of GCF and then combining. So I have my 2 factors that are the same. I'm going to cross out the first one, and so my final factored form is x plus 4, x plus 1. So there is our grouping example. Now let's go to our 4th method of factoring, which is going to be PST, or perfect square trinomial. If you remember, for our perfect square trinomials, it has to have 3 terms. That's what a trinomial is. And then both our first and last terms have to be perfect squares. Okay, and so now what we're going to do for the perfect square trinomial in order to factor is I am going to square root my first term. The square root of 4x squared is 2x. I'm going to square root my third term. The square root of 25 is 5. And so then my factored form is going to be 2x, 5, and then to decide what sign I put in between the 2x and the 5. I look at the sign here in the middle. Since that is a plus, I put plus, and then I just square that factor. The square means that the factor shows up twice, and an easy way to remember that is because it is a perfect square trinomial, so that factor gets squared. Our second example of perfect square trinomial, notice, is almost identical. If we square root, we get 2x. If we square root, we get 5. So if you notice, what is the only difference that you see here? The only difference is this minus. So instead of the factors being 2x plus 5 squared, the factors are going to be 2x minus 5 squared. So there are the two examples of perfect square trinomial. My fifth method of factoring is called difference of squares. And so for difference of squares, you can only have two terms, and they both have to be perfect squares, and they both have to be subtracted. Okay, so notice 9x squared is a perfect square, 25 is a perfect square, and we have the minus sign in the middle. So in order to factor difference of squares, I square root the first term, and I get 3x. I square root the second term, and I get 5. And my factors look like this. One is going to be 3x plus 5. My second factor is going to be 3x minus 5. For my last method of factoring, this one is called working backwards, so we abbreviate that as WB. And for working backwards, you need to have three terms, and notice you are not allowed to have a coefficient in front of x squared. So there's no number allowed in front of x squared. And how working backwards works is we need to figure out two numbers that are going to add to my middle number and that are going to multiply to my last number. Okay, so we're finding two numbers that add to 3, multiply to 2. Remember, the signs do matter. So if there was a minus, we want to keep that in mind. But my two numbers that add to 3 and multiply to 2 would be x plus 1, x plus 2. So I go ahead, write those, and there is my factored form. So this is all review from chapter 9. Hopefully we remember that pretty well. And now let's move into the new items here with chapter 10. So let's go ahead and use those methods of factoring to actually factor. Here in the top, we see my 6 methods, and you always want to use the process of elimination to decide which method we're using. For example, in example A, we know that it's not going to be a perfect square trinomial. Why not? Because my 6 is not a perfect square. I know it's not going to be difference of squares, because difference of squares only has two terms, and again, they have to be perfect squares. I know that it's not going to be grouping, because grouping requires 4 terms, and I only have 3 terms here. I know that it's not going to be combining, because combining, remember, they have to share the same factor, x minus 2, x minus 2. So my only two options that I'm left with are GCF or working backwards. Now for GCF, I can take a look at each of these terms to see if they share any factor. I don't see that they share any factor, but what I do see is that I have a trinomial and that there's no number, no coefficient in front of that x squared. So I'm not going to GCF, and so my final method of factoring here for example A is going to be working backwards. So for working backwards, I need two numbers that add to 5 and that multiply to 6. So we kind of think that through. The two numbers I come up with are 2 and 3, because 2 plus 3 equals 5, and 2 times 3 equals 6. So my final factored form for example A would be x plus 2, x plus 3. So there's my final answer for example A. For example B, I'm going to erase all the notations I made here earlier, because now again, we're going to start with our process of elimination and see which method is going to work for example B. So for example B, I know it's not a perfect square trinomial because it's not a trinomial. I know it's not going to be grouping because grouping needs 4 terms. I know it's not going to be working backwards because working backwards needs 3 terms. I know it's not going to be combining because they have to have the same factor in combining, and these don't in example B. So I'm left with GCF or difference of squares. And hopefully we can identify in example B that they are both perfect squares and they are being subtracted. So my winner is difference of squares. So for example B, the method I'm going to use to factor is difference of squares. How we use that is I square root the x squared, and I get x. I square root the 4, and I get 2. And so then my final factors would be x plus 2, x minus 2, and there's my final factored form. For example C, again, let me clear these notations that we made so that we can use our process of elimination. For example C, I know that it's not going to be working backwards because of this coefficient, right? In order to work backwards, I cannot have a coefficient there. Now, difference of squares. I can cross that one out as well because difference of squares only takes 2 terms. I can cross out grouping because grouping takes 4 terms. And I can cross out combining because in combining they have to share that common term. So I'm left with GCF or perfect square trinomial. Now you could potentially use either here, okay? So what we are going to do first is whenever you can do a greatest common factor, we want to do that first. So notice that all 3 of these terms can be divided by 4. So I'm going to demonstrate that here, just what it would look like. So for example, C is 4 times x there in example C. For the second term, it would be 4 times 8 times x. For the third term, it would be 4 times 16. Okay, so I'm going to GCF, this is going to be GCF, I'm going to GCF that 4 out. So I'm going to circle that 4 that they all have in common, and then in parentheses, I'm going to be left with x squared plus 8x plus 16. Okay? So whenever you can GCF, you always want to get that greatest common factor out first. Now our work is not complete because we can still either perfect square trinomial this or work backwards. I know working backwards is a little bit easier for us to think of, so we're just going to work backwards. We're going to now for this second part work backwards. Come up with 2 numbers that add up to 8 and that multiply to 16. My 2 numbers are going to be 4 and 4. So notice I'm going to keep my greatest common factor on the outside. And then for my factors, I'm going to put x plus 4, because 4 plus 4 gives us 8, and 4 times 4 gives us 16. So here is my final answer for example C. And of course, all 3 of these can be set equal to 0. We're going to see how that comes into play in a moment. Okay? So let's keep going. Here we go. What is the difference when the directions say to factor versus solve? This was so important on our Chapter 9 test. It's going to be so important here in Chapter 10 as well. So the problem, the problem may actually look the same. It's just going to be the directions and how we follow them. When we say to factor, remember that factoring is 99% of the time going to involve parentheses of some sort. Whether we GCF, whether we difference of squares, there's always parentheses in our answer. Whereas solving is going to have an equal sign. X equals 1, x equals 5. Okay? So factoring might look like this, x minus 1, x minus 5, whereas solving is going to have the equal signs in those answers. So let's solve this example here. And in order to solve, we do have to factor. So we're going to factor this by working backwards. Remember, there's an invisible -1 here. So I want 2 numbers that add to -1 and that multiply to -30. So again, give yourself some time to think. And the 2 numbers that we can come up with are -6 and 5. Because -6 plus 5 gives us -1. And -6 times 5 equals -30. Remember, the signs matter. So for example, 6 and -5 would be wrong because they don't add up to -1. So now that I have my two numbers, I'm going to factor this. X minus 6, x plus 5, okay? And remember, these are the factors. So if the directions said to factor, you would be done. But the directions don't say to factor, the directions say to solve. So in order to solve, I set each factor equal to 0. So I'm splitting them up. X minus 6 equals 0, x plus 5 equals 0, and now I'm just going to solve. I add 6 to both sides, and I get x equals 6, and then I subtract, oh boy. And then I subtract 5 over here, and I get x equals -5. Alrighty. So there we go. You see how now we have our solutions, right? These boxed answers are going to be the solutions when we are asked to solve. Okay, the red x minus 6, x plus 5 in parentheses, those would be the factors. Let's take a look now at quadratic functions. So a quadratic function means that you have to have a power of 2. So the function, which is just another word for equation, the function has to have x squared in it. So notice quadratic form looks like this. Y equals ax squared plus bx plus c, where a, b, and c would all be numbers. So we replace these with numbers, all right? So look at our examples here, examples a, b, c, d, and would they be quadratic functions? So I'm going to give you just a second here to think about that. And a few of these are tricky, but let's get started. I'm going to start with example B because that might be one of my more obvious ones. Example B is not a quadratic function, and the reason why is this x to the power of 4. Quadratic functions can only have x to the power of 2 as their maximum exponent or the maximum degree. So that's why example B is not a quadratic function. Example D is also not a quadratic function. Again, what is it missing? It is missing the x squared. In order to be quadratic, you have to have x squared. Okay? Now let's go to example A and C. So C is our lovely, beautiful example, right? It's almost textbook. It looks just like the format, ax squared plus bx plus c. Now, what are they using for a? They're using an invisible 1 for the number a, or for the letter a. They're using this number 8 to represent the letter b, and the number 16 to represent the letter c. So example C, yes, is an example of a quadratic function. Example A might be the trickiest, because we might be split down the middle if it's a yes or a no. But example A actually is a quadratic function, because the only difference is that the number in front of x, notice what we have here, 4x squared plus 0x plus 7. So it is still in quadratic form, it's just the number in front of x is a 0, so they are able to make that invisible. Okay, so here are some examples of quadratic functions, and now let's take a look at how we are going to use these. So quadratic functions are going to come into play with graphing a lot in this lesson, and so we want to talk about the parent function. Parent functions, when you see that term in math, or whether it's on the SAT, you'll definitely see it as you keep moving forward. The parent function is just the original function. So the original parent function for a quadratic equation looks like this, okay? It has this U shape. Now, for the original parent function as well, I want you to notice a few things here. Is where is this function beginning? This function is starting here at the origin, at 0, 0. Okay, and we call that the vertex. We'll talk about that a little bit more in future lessons, but that 0, 0 there is the vertex. And notice you can put this right into your calculator. What you would do is you would go to y equals This button is what we use for x. This caret is where we get our exponent, and then you would just do 2. So x caret 2, and then you would just hit graph. And if you hit graph, you'll see this graph right over here that I've already shown in the PowerPoint. Okay, so practice graphing that on your calculator because that's going to be a great tool for you to be able to see how these functions are working. We talked about this U-shape on the last slide, and this U-shape has a proper name in mathematics, and the name is a parabola. So the parabola is the graph of a quadratic function. So remember, quadratic meaning we have that x squared. So whenever you have an x squared, your graph is always going to be U-shaped. And remember here for the parent function, that vertex is at 0, 0. We're going to look at through the rest of this lesson what happens when that vertex is not at 0, 0. So let's look at our minimum and maximum. Like the names kind of insinuate, the minimum is going to be the lowest point. So notice over here in this parabola, my vertex is my minimum because it is the lowest point on the entire parabola. Now, could a parabola have a maximum? Of course, our answer is yes, it could. Notice over here, my vertex is still at 0, 0, but it is now the highest point of the parabola. So this would be an example of a vertex being a maximum. And notice how we would get this graph is by graphing y equals negative x squared into our calculator. So try that as well. Go into your graphing calculator, go to y equals, and put negative x squared so you can see those differences in the graphs. All right, guys, let's get to our examples. I know this first PowerPoint's a little bit long, but thanks for hanging in there with me. So our first kind of activity example here is, again, in your calculator, go ahead and graph y equals x squared. If you do that, you should get a graph that looks like this. And what do we call this graph? Okay, this is very important vocabulary. This is called the parent function, right? This is the parent function that starts at 0, 0, gives us our traditional parabola opening up. Now, for the second part, go ahead and graph this in your calculator. And if you do that, then you should have a graph that looks like this. Okay? Notice, what is the difference? The easiest way to tell the difference is to find your vertex. What has happened to the vertex? Here my vertex was at 0, 0. Now my vertex is at 0, 1. So how did my vertex move? It went up 1. Okay, and we call that a transformation because now our parabola has moved up 1. Let's look at our second example here. So we graph our parent function, that y equals x squared. We get this graph with the vertex at 0, 0. We graph our second function, and we end up with this graph. Again, to see the difference, let's find that vertex. In my second graph, notice the vertex has now gone down 1. And do we have any conjectures already as to why? In my previous activity, notice my second one said +1, right? In step number 2, it says to graph x squared plus 1. Now, I'm graphing x squared minus 1. And so that's why in the last activity we went up 1, in this one we are now going down 1. Give me one moment. Our little PowerPoint app seems to have frozen. Maybe if I want to get fancy, I'll edit this out for you so you'll know if I did or not, whether it's still here. We're almost done. This lesson doesn't go all the way through. And so here we are, guys, on our next activity. I believe we have 2 more of these, and then we'll have our final summary slide, because we are looking at these transformations and what is happening to our parabola and our parent function. So here we have y equals x squared. Again, that's my parent function. If you graph that in your calculator, you will get a parabola that looks like this with my vertex at 0, 0. Now notice the second function that I'm graphing. Now I have parentheses involved. Y equals x plus 1 in parentheses squared. If you put that into your calculator, you get this graph. And again, let's find that vertex and notice what happened. It went to the left 1. And what is dictating that is this plus 1 on the inside. Okay, if it was plus 2, it would have gone to the left 2. Here in my next activity, notice I graph my parent function again. It looks like this. I have my vertex at 0, 0. I graph my second function. Notice now I have x minus 1 in parentheses squared. And what happened to my vertex? It moved to the right 1. Again, this is being dictated by that minus 1 inside of the parentheses. Now, normally, a minus 1 would make us think that we're going to the left, but it is going to be the opposite. And we'll talk about that a little bit more on our summary slide. But whenever you have something in parentheses, a number in parentheses, it's actually going to be the opposite. X plus 1 moves you to the left. X minus 1 is going to move us to the right. So here in our activity, and I believe this is our last activity, let's go ahead and combine a few of the different transformations we've looked at. Again, you always want to start with the parent function because you need to have something to compare it to. If you don't have that starting point, that original function, then you don't really know what changes have occurred. Now, if you graph this, we have a lot of different things involved. So if you put that into the calculator, you're going to get this graph. But notice instead of my vertex being at 0, 0, my vertex is now at negative 2, 1. And so where do we think that came from? Notice this means that I went to the left 2 and I went up 1. This plus 2 is what moved me to the left. This plus 1 is what moved me up. Now, what else did I do? I am also now upside down. And this negative is what flipped me upside down, what reflected me over that x-axis. So notice that our equations can get a lot more complicated, right? It doesn't just have to be plus 1, minus 1. We can incorporate all of these different transformations into one equation. So let's look at our transformation rules here as a whole. This summary slide is super important, guys. This is our last slide here of the PowerPoint. Okay, and let's talk about modifications that we can make to the parent function. Remember, these are all transformations that we are making to this parent function. So this was the first activity we did, and notice we added outside parentheses. This is going to be very important because if you are outside parentheses, it is a vertical translation that is moving you up. Okay, remember vertical moves you up or down, just like think of your vertical blinds in your house, that kind of thing. Okay, or even in sports, right? If you have a vertical, it's how high you can jump. So our second transformation rule is if we subtract outside the parentheses. And again, anything outside parentheses is going to be a vertical transformation. And if we subtract on the outside, we are now moving down. Okay? If we add inside parentheses, remember inside parentheses is when we talked about things being opposite. Okay, when we have numbers inside parentheses, everything is to the opposite. So a horizontal translation where you add, it is actually going to move to the left. Okay, so this plus 1 is actually going to move us to the left because it's the opposite of what we would normally think it is. If you subtract inside parentheses, then you are going to move to the right. Okay? And then our last one here, which we looked at in the last activity, is if we put this negative out in front. So if we're multiplying by any sort of negative, it can be -1, -2, any negative number is going to be a reflection or a flip, right, over the x-axis. So this is our summary of transformation rules. Please pause this lesson here on this slide, especially as you do your homework, because this slide is going to be extremely important in helping you answer those homework questions, particularly the last 4 questions on your homework. So that takes us to what your homework is. Your homework has been posted in Google Classroom. So if you log into Algebra 1, then at the top you should see a tab for classwork. Go to classwork, and then you'll see chapter 10 homework. So there you'll see the homework that goes here with 10-1, day 1. I have uploaded the PDF, okay? You will need your factoring table, so you can find the factoring table in Google Classroom. If you have yours as well, you can also use that. And this is what the homework will look like, okay? In Google Classroom, you'll see the homework looks just like this. You'll do these first 5, which are a little bit of factoring. And then you'll do these bottom 4, where you're going to tell me what transformations took place. Okay, guys? So thank you so much for sticking with me through this kind of long first lesson here. But let me know if you have any questions. Just post them in Google Classroom so that I can answer your question and hopefully help your classmates as well. So thank you so much, and I will see you guys at our next one.